This is an introduction to exercise 9L and exercise 9M on limits and continuity, and also when a function is differentiable. Very quickly, a quick review of limits. Again, some of you guys should be generally quite familiar with, especially because we covered it quite in depth last year. But these are the rules that are applicable where both limit of f of x and limit of g of x exists. They're quite similar to a lot of the rules you've seen before, but you can add them, multiply them, multiply with a constant, multiply with another limit, or you can divide them as well. Just following these rules, but they're pretty much the same as what you already know. We're going to jump right into the examples, because again, limits are something that we're quite familiar with. I'm going to go with question B first, because it's more familiar of a format. So with question B, find the limit of the value where x is approaching -2, where we have x squared plus x minus 2 over x plus 2. Now, what is the problem with me just substituting right off the bat x equals to -2? Why can't I just substitute x equals -2?
Because the denominator... Wait, is this the first question?
Second question. No, you're right.
The denominator equals 0.
Good, exactly right. If I substitute x equals to -2 off the bat, we would end up with a value of 0. Well, not 0, sorry. We'd end up with 0 in the denominator and end up with a value of undefined. So instead, what we can do is completely factorize as much as we can and then substitute it, which would avoid the divided by 0 aspect. Again, I'm going to write limits as x approaches -2. I do apologize for the font being so thick. Let's change that. There we go. Alright, so the limit as x approaches -2. And I've got, now I'm going to actually take to the side. You're more than welcome to do this in an assessment. I'm going to say that x squared plus x minus 2 is equal to, and I'm going to try to factorize it using cross method. I'm going to say that x times x gives me x squared, and -2 and +1, they multiply to give me -2. Is that the right answer though? Why not? Good, reverse the negatives. You guys are expert at that. That way, still multiply -2, but they add to give me positive x. Awesome. I know they give me x plus 2, x minus 1. So I'm going to rewrite that here, replacing that. So I'm writing x plus 2, x minus 1, all over x plus 2. And then, I'm going to rewrite that limit as x approaches to -2. We have to keep writing it, unfortunately. And we cancel those out, and we end up with x minus 1. If you would like, you're welcome to do all the calculations on the side. So I'm saying take out the whole fraction on the side. And then at the end of that, so once you factorize that, bring it back into the limit of x, blah, 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 so that you don't have to write limit every single time. You're welcome to do that as long as your working out is logical and follows a logical pattern. Do I just leave my answer there? Good, substitute. So we're substituting x as -2. So we get -2 minus 1, which gives me -3 as an answer. Awesome. Oh, this is page 3 of your booklet, apologies. Alright, now we're going to jump up to this one on top. So find the limit as x approaches 2, where we have a graph, that's made up of different functions. So in this case, what are the two functions we're focusing on when we're saying x approaches to 2? Good, we're focusing on the bottom two. We're focusing on the bottom two because the first one is only when x is less than or equal to 0, so we can ignore that for now. Let's try to find the limit as x approaches 2 for x plus 2. Well, of course, I know that there's no further factorization that can occur, so I can just substitute that in. 2 plus 2 gives me 4. Now, just to double check, I'm going to do the same thing as x approaches to 2 of x squared. So it's still towards 2, but it's on opposite end. I'm just going to double check. And we end up with 2 squared, which gives me 4 anyway. So the limit of all this equals to 4. As x approaches to 2, apologies. Seems like revision. Everyone's on top of this. Awesome. I'm going to jump into continuity. Again, stuff that you guys already know, but more so just a quick revision. Continuity. A function has to be, or is considered continuous at a specific point if the following conditions are met. And these two conditions are very important. I definitely recommend you guys writing them into your resource book. If f of x is defined at x equals to a, what does that mean? Well, it just means that the graph has to exist at x equals to a. Of course, it makes sense. If it doesn't exist at that point, then it's obviously not continuous. So if I was to substitute 3, then the function needs to exist at that point. The second thing is that the limit as x approaches to a for f of x must be f of a. If I approach the same value from both ends, so from the positive and from the negative, then it should give me the same answer. Otherwise, it's not continuous. In this example here, these hopefully seem very familiar to you guys. I'm not going to write it out, but I'll tell you guys what we should be looking for. In this example, is f of x defined at x equals to a? So when x equals 1, does this graph exist? Does this function exist? Is there a y value when x equals to 1?
Oh, yes,
There is.
There is.
Right there, it is.
Are you able to print off the Mac desk? Miss Books?
Could you find someone else for me? I'm in the middle of
sorry.
teaching. Thank you.
She asked me if you need that. So.
That's okay. Thank you. So we're looking for this. We're saying, okay, we've got this point. It does exist. The graph does exist when x equals to 1. It's not part of it, so automatically we know it's not continuous. But how will we describe it using mathematical notation? We say the f of 3 is defined. However, the limit as x approaches 1, so I would write, for example, limit as x approaches 1 of f of x does not equal to f of 1. Because f of 1 should be at 2. However, the limit as it approaches it is at 3, sorry, my apologies. But the limit as x approaches 1 is 2. So the values are different and therefore it is not continuous. Yeah? In this example over here, similar idea with this one right there. I know that when x equals to 1, the point is right there. However, if I take the limit as x approaches 1 from the positive end, then it's going to give me a value of 3 instead of 2. Similar idea over here. If x equals to 1, a negative 1, my apologies, f equals negative 1, then I know that the graph will approach 2. However, if I go from the positive end, it'll give me negative infinity instead. Okay? So, identifying continuities, you have to use specific terminology and relate it back to these two rules. It's highly likely that you'll see a question, perhaps in the multiple choice, that'll say, this graph is discontinuous, or it has a discontinuity at, and then you have to choose x equals 3 because blah, 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 blah. So understanding why something is discontinuous is important. Hi.
We just needed to
Go for it. Alright, differentiable. So when a function is differentiable, of course it means that the limit as h approaches 0 must exist for this. Is that formula very familiar? Good. That's the first principle formula, of course. And we're saying that, for back to the first principle, a function is only differentiable when there's a quote-unquote second point to make. So hopefully you remember first principle is saying that we have a first point, a second point, and we make that gap small and small and small and small and smaller. Of course, if I give you a graph, for example, where the graph looks like this, it's differentiable for all these parts here, here, and here. But at that point right there, exactly on that tip, it's not differentiable. Because it's not a part of either function. It could either be this way or this way, we don't know. So it's not differentiable because there is no quote-unquote second point to get that gradient from. A function is differentiable at a point, then, sorry, if a function is differentiable at a point, then it's also continuous at that point. It makes sense. In this example, instead of going and answering these questions as a class, I've shown you the answer here, and I'm just going to explain it. In this situation here, the questions ask for if we define f dash x, and then sketch the graph. Very easy. All we have to do is identify, for example, in this case, x is greater than or equal to 0, and therefore the graph will be x squared plus 2x plus 1. Using the differentiation rules, we know that's 2x plus 2 as a formula. So we just graph that from there to there. And of course, 2x plus 1, the derivative would be 2. So we just draw that graph there. And the same thing applies here, except we've got a different situation. Where at x equals to 0, there is no derivative. So in this case, it'd be 1. In this case, it would be 2x plus 2. However, it doesn't line up. So those graphs don't line up, and therefore, there is no gradient in between. It's discontinuous. Any questions? No? Awesome.